received an email from me with your grades? Okay. And so a couple people I got email bounce back, so something's wrong with the email server or something. But most of them should have gone through. You should have gotten an email. I think there's a couple people that didn't get emails from me, but most of you should have. It should have your homework grades, the quiz grades, and the midterm grades. Okay. Your total grade is determined by what is it? 15% homework, 20% quizzes, 30% midterm, 35% final. Okay. So the midterm weighs quite heavily. Some of you, maybe your midterm score was not as good as you had hoped. As I was grading through the free response section, I know a lot of people missed the questions that use the binomial table or binomial model, and then several other mistakes and things of that nature. There's still a lot of work out there. Okay, we still have 2 more quizzes. We still have a few more homework assignments and a final exam. So anything can happen. Okay, your grade, you can bring up your grade. Your grade can go down. Anything is still possible. But if your grade is poor, like a D or an F at this point, there's work that needs to be done. And so are there any questions regarding tests and stuff like that? Yes.
Did you include in the email if you got the bonus right?
The bonus point on the bonus problem on the test? Yeah, that's already included in your midterm score.
So, but you didn't separately write that?
I didn't write it in a separate thing.
Oh.
That would have gone into the free response section. Okay, so if you got all the questions right in the free response section, you would have gotten 35 points in the free response. Okay? Alright, so yeah, the highest grade on the midterm possible is 110%. I think the highest we had was 106%. After the progress report out, 85 students enrolled, about 80 students took the test. Okay, so I think about 5 students have already dropped, and 23 students have an A. Okay, so a good over a fourth of you have an A, which is good. A good number have B's. There's some C's, and then maybe a few more F's than I would like, but some of you are not doing that well. So that's a friendly ringtone. Certainly make sure my own ringtone is turned up. Okay, so that's that. I believe the midterm was the appropriate difficulty in terms of how this class's grade performance is compared to previous quarters. Similar, so some who do well, some who do poorly, a lot of people in the middle. Okay, the average was about a 73%. Okay, but that's the mean. Okay, which we know is affected by outliers. Okay, and so it is a left skewed distribution with some outliers very low, bringing down the mean. Okay, but I didn't actually do calculations on the median, but the median is higher. Okay. So if that made sense to you, you probably did fine, and if that part didn't make sense to you, then maybe you're part of the reason why the mean went down. So okay, I know some people are already looking towards the final exam. All right, the final exam is going to be all multiple choice, and it is cumulative, but in the sense that it is heavily heavily test stuff from this point forward with a few questions on previous material. Okay, so previous material will be a lot less calculation heavy. The calculation parts will pretty much all come from this point forward. Yes, question? I'm sorry? Yeah, if you get all the questions correct, you will get 110%. I'm very generous with getting extra points on quizzes and exams. Okay, so I know some students complain about grading being harsh or something, but I feel like I'm very generous with the bonus points I give on quizzes and exams. Okay, I don't believe in giving extra points for some mindless activity that you can just do at the last minute or something. Okay, so you got to work for your extra points if you want them. But yes, there will be extra bonus points on that as well. Okay, so we'll worry about the midterm. The final exam as that approaches. And today we will move on to chapter 7. Next week you do have a quiz. Okay, these quizzes, a lot of you are counting on them to help you boost your grades. So please study. Next week's quiz is pretty much going to all be from chapter 7. Okay, what we're covering today. So study it well and make sure you understand. All right, so let's get into this. Okay. Now everything we cover builds up on previous stuff. So chapter 7 stuff builds up on our understanding of the normal distribution, okay, from before. The binomial and the normal distribution. Our understanding of chapter 7 builds off of that. So I hope you guys are comfortable working with z-scores, looking up values and percentiles in the z-table and things of that nature. Okay? I know a lot of you missed those questions on the normal distribution on the exam, so please make sure you really understand the normal distribution, because if you don't have that down, the rest of this quarter is going to be quite miserable. Okay? Alright, so when we first started statistics this quarter, what did I say statistics is all about? It's all about data, but why do we bother studying statistics? We are trying to make conclusions based on limited data. Thank you. Okay, so we're still aiming towards that. Okay, so we want to make conclusions and what does it mean to have limited data?
Like not a lot.
I'm sorry?
Like not a lot.
Not a lot? Okay. Anybody else want to expand on this idea of limited data? So we are not dealing with the population. What is the population?
It's the whole.
Population is everything that we could possibly want to study. We don't have all the information from the population, but we do have a sample. Okay. So limited data, basically we're referring to, we are working with a sample. And a sample is pretty much any set of data that we have that we can observe. And based on this sample, we want to understand and make conclusions about the population based on the sample. Okay? So by studying the sample, we want to understand something about the population. this is a very basic but important concept that we need to understand. We want to know how much TV the average American watches. We can't interview every single American in the United States. But we might be able to ask 1,000 people. Okay? Based on what we see in the 1,000 people, which is our sample, we might be able to infer something about the population, about all Americans in general. Okay? All right, so this is called inference, sampling inference. Or we'll just call it inference. It's basically drawing conclusions Okay, so let's say we want to know, maybe we want to know what percentage of Americans, of U.S. adults, have a college degree. So let's say we want to know what percentage of Americans have a college degree. Now, if I asked you, so what we're going for, okay, percentage of U.S. adults, this is the quantity that we want to know. Guesses as to what this percentage is approximately? I think it's like 27%. Okay.
Really?
Huh?
Really?
You think that's too high or too low?
Too low.
Too low? Too low? All Americans, okay? So that's, you know, we live in Southern California, and you guys are in college right now, so probably your peers, a lot of your peers have college degrees, but there's a lot of people where their social circles and things like that don't have college degrees, okay? And this is also including a lot of senior citizens, everybody out there, okay? But this quantity that we want to know, is this something that describes a population or a sample?
Sample. Population.
Yeah, it's all U.S.
Yeah, U.S. adults, right? So, U.S. adults, what is their population? Our population is U.S. adults. Okay. And this percentage, it's a quantity that we want to know that describes our population. This is known as a parameter. So the parameter is the percentage that we want to know. Okay? A parameter is basically a number or a statistic or something that describes the population as a whole, okay? So if somehow we were able to survey all U.S. adults, okay, all 200-something million U.S. adults, and we asked every single one of them, do you have a college degree, yes or no? Some people will say yes, some people will say no, all right? And we can get the actual percentage, right? So let's say there's 230 million U.S. adults. I don't know how many there are. Okay, there's 300-something million people in the U.S., but a lot of them are not adults. So let's say there's 230 million, and let's say exactly, I don't know, 51,685,422 say they have a college degree, right? So let's say 50,000, what did I say? I don't know, 50,600,422 have degrees. Out of, let's say there's 231,621, 886, okay? So let's say this is how many US adults total. Then we can get a percentage, and this is the true population parameter. Okay, whatever this percentage turns out to be, this is the population parameter. Is that okay? Does that make sense? However, is there ever going to be a situation where we know exactly how many US adults there are and how many have college degrees?
Not exactly.
No, it'll be almost impossible. It'll cost a lot of money just to get these exact numbers, okay? But we would get an exact population parameter, okay? But then the next day somebody will die and somebody will graduate from college or something, and these numbers will change, right? So, yeah, or somebody will drop out of college, but then they never had the degree anyway, whatever, okay? These numbers will change on a daily basis or near daily basis. Yeah, no, US adults changes on a daily basis. And so our population parameter changes quite a bit, okay? But this will give us many, many, many decimals of precision, but we probably don't even care after, you know, the 7th decimal place, okay? We probably don't. So what we're going to do is we're going to deal with a sample instead. Instead of trying to get this exact population parameter number, we're going to try to estimate it using a sample. Okay. So with inference, okay, we want to estimate the population parameter based on a sample. Alright, so let's say my true population parameter really is this. What is my 422 divided by 231,621,886? Okay, so this is probably lower than it really is, but so this is 0.218. Alright. Okay, that number's probably much lower than what it really is, but whatever. Okay? I'm sorry, I'm going to just modify this, just so it ends up being a little bit better. Let's just change it to 60. Rather than 50, let's change this to 60. Okay, so if I change this to a 60, 60,683, 422 divided by 231, 621, 886. Okay, this is 0.26. Okay, so that might be our population parameter. I'm just making up a number. Okay? So, we want to just estimate that. So, what do we do?
We take a sample?
Yeah, we take a sample. Okay? So, we take a sample. Now, how should I take a sample?
Random.
Yeah. Okay, so how can I take a random sample? Take a sample, a random sample. Any ideas on how we can get a random sample of Americans? You have an idea?
Ask the first 100 people you see in each district, based on 1,000, I don't know.
So I go on the street and I just start asking 100 people?
Yeah.
Would that give me a random sample?
Yeah.
No, it won't. Because why? It depends where I go, right? If I walk out the door right here and I ask 100 people, and I say, how many of you have a college degree? Okay. Well, the people I'm asking will be college students, right? So, what's that? Okay, so is there any place in the U.S. that I can go that'll give me a diverse group of people that will represent the United States? Let's say, huh? The census. Okay. Well, the census doesn't really give us a sample. It gives us everybody. Yeah.
If you go to like multiple districts, 100, 10 different districts, find out 1,000.
Phone book?
Okay. So go visiting different districts, 10 different ones. How do I pick these districts?
Random.
Pick them out of a hat. What's a district?
I don't know.
It's hard, right? It's hard to come up with a way to get a true random sample. Okay. We can look in the phone book, but that's only going to get people listed in the phone book. How many of you are listed in the phone book? Yeah, maybe your parents, maybe some of you are listed in the phone book, but a lot of you probably aren't. Okay. So getting a random sample, all right. I know a lot of these problems talk about getting a random sample, but this is actually difficult, all right? And we will talk about sampling methods and things like that later on. Companies that try to get random samplers, they use robot random digit dialers, okay? That's probably random dialer. Basically, it just punches in a bunch of different phone numbers, right? It just says, okay, I'm going to call 621-538-7429, and then it'll see if somebody picks up, okay? And it gets, that's pretty good, okay? It gets a pretty good random sample that way, all right? Because you can end up calling anybody, and it's about 98% of Americans have access to a telephone, okay? So, or 90, it's pretty high. There's just a few people who don't have a phone, whether it's a cell phone or landline, okay? But yeah, it's a complicated process, okay? Taking a random sample. But anyway, let's say we get a sample. Let's say I called 1,000 people. I kept getting random people, and then so I get 1,000 random people. And let's say 271 graduated college. Okay, so what is the proportion? What's my estimated proportion based on my sample?
Well, 271 is 100,000.
Yeah, 271 over 1,000 gives me 0.271, or 27.1%. This is my estimate based on a sample. Okay. Or we call this our sample proportion. And this is a statistic. So that number up there, what was this called? This 0.261993471? That's a population parameter. This number here, 0.271, this is a statistic. It's a sample statistic, or in this case, it's the sample proportion, but it's a sample statistic. Okay? Because these are both proportions, but that one describes the population, and this one comes from my sample. Is that okay? Now, is this a good estimate of that number? So we want to estimate that number, right? Because we're gonna pretend like we don't know that. Actually, we don't, right? So we don't know what the population parameter is. So you asked 1,000 people, and you get 0.271. Is this a good estimate of the population parameter?
Yeah.
Yeah? No? What do you, some of you are nodding your head. Some of you are shaking your head. What's your reasoning behind your action here? You guys understand what I'm saying?
Right.
Okay, so it's a little bit off, right? It's not exactly that, but it's close. It's close. Okay, so that's pretty good. Okay, but what if somebody else, you know, some other company goes out and they conduct a sample, right? They call another 1,000 people. Okay, so let's say, let's say they called 1,020 people. And let's say 264 have college degrees. All right, what's the sample statistic here? Yeah, 264 divided by 1020. This gives me a different number. And this one is 2.2588. Is this any good?
Yeah. It's close.
It's still close.
It's close. It's not exactly. And which one's better?
That one.
The first one.
Yeah.
Or would we have any idea, right? So let's say this is unknown, right? We're pretending like we know this. But in reality, we don't know the population parameter, and that's why we're conducting samples to begin with, right? We're going out and we're interviewing 1,000 people. This is a long, tedious process, but we think it's important, so we go out and we do it. And one guy comes back and he says the proportion is 0.271. Okay, and then the other company comes back and they said the proportion we got from our sample is 0.2588.
But isn't it good, like, if they both, like, are close to that? So
Yeah, I mean, they're close to that, okay?
Yeah.
Okay, all right. So I mean, because we have an idea of what the answer is, we can kind of decide what's good or bad, right? But in reality, let's say we have no idea what the answer is, okay? So we see this and we see this, and let's say somebody else takes a sample of 1,000 people, and let's say, is it possible that if they survey 1,000 people, that the number of people who went to college was 238? Is that possible?
Yeah, it is.
Okay, so now their sample proportion is 0.238. This is their sample statistic. Is this a good one or a bad one? Now we have no idea, right? In all of these situations, somebody's coming back, they said, I interviewed 1,000 people. This is how I got my random people. I went to 20 different districts asking 50 people. I called 1,000 random phone numbers. I used this method to get things, and we're getting all numbers that are kind of close, but they're all different, okay? So based on this, can we say anything about the population? If we have, right, I cheated and I gave you the answer, but in reality, this number, we said there's no way for us to interview that many million people, so this is what we have to deal with. What can we do with this?
You can multiply it to get to that number so we can get the closest. No?
Compare it.
If you want to know if it's that number.
Okay, well, all right, well, I mean, we could combine all of them, right? We can say, okay, well, in reality, we interviewed 3,020 people, and we get maybe another number that maybe is a little bit better, okay? But we still have no idea what the true value is, okay? All we can say is, well, the true value is probably somewhere around here. That's the best we can do at this point, okay? All right. So we'll put this problem, put this idea in this scenario, I guess, put it on hold in your brain, and we'll try out another scenario here, So let's say, we want to understand this thing, and we say, well, every time I survey 1,000 people, my proportions are a little bit different. And I don't know if these proportions are any good. This is kind of the situation we're in right now. Okay? So someone says, all right, I've got an idea. Let's try to understand how different proportions can be. Let's try to understand. Okay, so the guy is saying, every time I survey 1,000 people and ask them how many times, who went to college, I've done this 3 times already. The proportions all ended up a little bit different, okay? And I don't know if any of these are good numbers or not. Okay, so can we understand how much our proportions might vary from one sample to another? Okay. We want to understand how much our sample statistics and what is our sample statistic? In this case, it's our proportion, right? Our sample proportion. Can vary each time. Alright, so does this make sense? Kinda? Alright, so someone says, okay, let's try to understand this. Alright, and what we're going to do, we're going to simulate something like asking if somebody went to college or not, but rather than having to actually find people and ask them questions and make sure that they're okay with participating in a study, which takes a long time, let's just deal with some M&Ms, and this will make our life a little bit easier. Okay? So let's say I have a giant bucket of M&Ms. So let's say I went to Costco, and let's say I bought 20 bags, 20 of those giant party bags, and I just dumped them into here. Okay? So maybe I've got, I don't know, several thousand M&Ms inside here. Okay? This bucket represents my population. Population of M&Ms. And let's say, is that okay? And let's say I take a sample. I get a scoop, and I take a sample, and I make sure that there's 120 M&Ms in there. Okay? Sample has 120 M&Ms. Alright, and our first sample, let's say we're looking at green M&Ms. Okay? Let's say 20 are green. What is my sample proportion? 20 out of 120, okay? So I'm going to write p hat. This is the proportion coming from my sample, okay? There's a hat because it's an estimate. Remember when we did regression, we said hats mean estimates. This is kind of an estimate of what the population proportion is, okay? So here I've got 20 out of 120, so this is 0.1667 green. P hat. So based on this thing, what is the parameter that I'm looking for? Yeah, so the parameter so our parameter P is the proportion of M&Ms in the population that are green. Okay, that's what we're going for. And this sample is an estimate of that. Okay? And that took us, maybe it took a minute to do, to count all those things up, a couple minutes. And then we dump those back in and we stir up the pot. And we do this again. I take another sample. N equals 120. And let's say this time 18 are green. Okay? So now my p hat is 18 divided by 120. That's something else. What is that? This is 0.15. Okay. I put that back in. Let's say I reach in there and let's say this time, again, each time I'm making sure I have 120 M&Ms, and maybe this time I get 24 that are green. Okay, and so now my p hat is 0.2. Is this okay? And let's say I repeat this 1,000 times, or I repeat this maybe 10,000 times, okay? I can do this over and over and over again. Yeah, every time it takes me a few minutes to do it, but it's better than having to go out and survey 1,000 people, okay? So I can do this over and over and over again, and every time I get a different p hat. Sometimes, maybe another time I draw 20 M&Ms, okay? And so maybe I get 0.1667 again, okay? And maybe another time I get 21 out of 120, and in that case I get 0.175. Okay. And is it possible for me to get 120 M&Ms where only 10 are green?
Yeah.
Is that possible? But how often do you think that will happen?
Very rarely.
Very rarely, right? But it's possible, okay? So maybe once in a long, maybe after 1,000 times I do this, maybe once I get p hat equal to 10 out of 120, which is 0.0833, okay? Maybe this happens once, okay? This will probably happen quite a bit. This will probably happen quite a bit, okay? All right, and if we do this, so I'm keeping track of all the different p hats. Every time I take a sample, I keep track of all the different p hats. Let's say I do this 1,000 times, so I have 1,000 different p hats. And let's say I make a dot plot or a histogram. Okay, what do you think this histogram is going to look like? Yeah. So, all right. So, what do you think? Do you think it'll be unimodal? You think it'll be bimodal? You think it'll be symmetric, skewed? What do you think?
With these numbers, or if you have to?
Yeah. So, let's say I keep drawing out samples of 120 M&Ms over and over and over and over and over again. Okay. Okay. Well, probably some of the values will show up quite a bit, right? If my very first sample I drew 20 green out of 120, it's very possible for that to happen again, right? I can very easily draw another 120 M&Ms where I get another 20 green, okay? So I might get something that looks something like this. And we have a question.
Yeah. So are we saying that there's as many green M&Ms as brown, red, yellow?
That doesn't even matter. That doesn't even matter.
It doesn't correspond to the previous population thing.
I mean, maybe, but that's not what I'm going for. Okay. right now, for some reason, I have an obsession with green M&Ms, and I just want to know what proportion in this giant bucket are green.
Okay, so it doesn't explain the other problem.
Yeah, yeah. It could even be like holiday something, you know, I don't know, they do like Easter M&Ms or something where it's like pastel or something, whatever, right? It doesn't matter, okay? Yeah. Or you can custom order M&Ms for your wedding now, and they'll have like things printed on them, right? So, if you really like M&Ms, right? So, all right. It turns out we get something that looks a lot like the normal distribution. What do you think? What value goes in the middle here? What do you think? Yeah, the mean.
Well, the number that
Yeah.
appears the most.
The number that appears the most turns out to be the population mean. Okay, so let's say this thing was actually 0.1742 proportion green. Okay, so let's say there's 10,000 M&Ms here, and exactly 1,742 are green. So my population parameter is 0.1742. Okay. Now I will never actually get 0.1742 as one of my sample proportions. Why not?
Maybe that's like the fourth.
Yeah. Okay. Because I've got 120 M&Ms, right? So I could get 20 that are green. I can get, if 21 are green, I think that's what this is. Or not. Yeah. So this is if 21 are green, I would get 0.175. Okay. So when I count up how many M&Ms are green, I'm either going to have 20 are green or I'm going to have 21 are green. Okay. I'm not going to say 20.2 are green. Okay. Maybe I have a deformed M&M, but we'll just not count these things, and we don't count those as half M&Ms or something. Okay. So none of my samples will actually be 0.1742, but probably what's going to happen is I'll probably see quite a few times out of 120 M&Ms, 21 of them being green, okay? So in the center, I will have something very close to 0.1742, okay? And sometimes I will have more than that. So sometimes my proportion that's green will be higher than 0.1742. Sometimes my proportion green will be lower than 0.1742, okay? But do you think I'll ever draw 120 M&Ms where all 120 of them are green? No. No. Is it possible?
Yeah.
Just from random chance?
Yeah.
Yeah, maybe, okay? Huh? If you order all green, right? But if we're just talking about a random assorted thing of M&Ms and you're stirring the thing up, okay? Like theoretically, it's possible to get something that's all green. But you're much more likely to probably win the lottery 3 times in a row for your bucket, your scoop of M&Ms to end up being all green, okay?
Only during Christmas time it's all green.
It's half red, half green for Christmas, yeah?
90%.
So even then, it's going to be difficult to get all green, right? You're only going to get all green if somebody has obsessively been picking them out, okay? But, you know, because we could, let's say, what would be the probability of getting all green if this was my,
0.
how could I calculate that? All 120 M&Ms have to be green? I would do 0.1742 raised to the 120th power, right? Come on, you guys. Right? We learned this? We learned this? Yes? Okay, 0.1742 to the 120th. If you try to do that, it's going to come out to be very close to 0. It says 8.42 to the times 10 to the negative 92. Okay, you've got 92 zeros and then an 8. Okay, so you got 0.0000. You got 92 of these zeros, or 91 of them. 91 zeros and then an 842. Okay, that's what this calculator says. Okay, 842. You got 91 zeros. So pretty much not going to happen ever. Okay. but theoretically, it's possible.
I
Okay?
know one place where it is possible.
Huh?
The M&M factory in Vegas.
The
You
M&M.
can pick any colors you want and fill your own bag.
Yeah. Okay. But we're talking about the population of M&Ms as my bucket. Okay. So yeah, if you go to Vegas, yeah, you can get a green. I have not, but I've seen it. I walked past that building where the giant M&M
Exactly.
dude is there. Okay. Yes, so it's certainly possible, but anyway, we're talking about, but you guys are talking about manipulating the population. Here I'm saying, let's say I'm just scooping things out of my bucket, okay? Which is what we're doing here, right? Because that's what, this is like a illustration of what we're trying to do with the population of the United States, right?
Right.
We're trying to get an estimate of how many adults have college degrees in the United States, and so the United States represents our population, and we're drawing random samples. Okay, we could manipulate our samples so that we're only going to some college graduates convention thing. Okay, yeah, if we take a sample at UCLA Reunion 20 whatever, we could yeah, then it'll say, oh, 100% of the people I surveyed went to college. Okay. But we're changing up the population there, okay? So not what we're trying to do. All right, so anyway, this is what we've got. But we want to know how much variation is there, okay? So it turns out this thing looks very similar to a normal distribution. Exactly a normal distribution, but we're going to just pretend that it is. And the only difference reason why it's not is because the normal distribution is continuous, but like I said, the M&Ms, you're only going to have 20 green or 21 green or something, and so your proportions are limited to certain numbers. So it looks very similar to the normal distribution, and we're going to say the mean of this normal distribution is equal to P, which is the proportion in the population. The population proportion. Okay, and the standard deviation, I'm just going to give you the formula, is equal to the square root of P times 1 minus P over N. P is still our population proportion, and what is N? Number of numbers. This is our N is, yeah, our number of numbers or our sample size. Okay. So in this case, if I'm drawing samples of 120, P is 0.1742, and my N is 120. So I will have a normal distribution. What is the mean of my normal distribution going to be? The mean is 0.1742. Okay, not a trick question here. And what's my standard deviation? Sigma is square root of 0.1742 times 1 minus 0.1742
Over
divided by
120.
120, okay? This is a good opportunity. Please take out your calculators and make sure you know how to calculate this value on your calculator, okay? Because I'll put the answer up here, and then you can decide if you know how to use your calculator or not, okay? I'm not trying to like make fun of you or anything, but I see a lot of students get this far, and then they punch it wrong in their calculator, and it just throws everything off for the rest of the problem, you know? And it's unfortunate, but sometimes that happens. So please make sure you can get the proper result on your calculator. All right, so if I keep a whole bunch of decimals, I'm getting 0.043623. get that?
I only have two.
Let me just make sure that I did it right. Maybe I did it wrong.
You need to write it. I thought I got it. Isn't it 4?
I have a math.
0.034623. Yeah, that's what I'm
Don't
getting.
you turn it into a 4? Since there is a 9 after the 4.
I'm getting a 2349.
4, 9, that becomes a 5.
So if I'm rounding here and I drop here, this number after is a 4.
If you round, doesn't the 4 turn into a 5 and then that turns into a 4?
So if I round here, then this would turn into a 5.
Right?
But if I'm rounding here, I have a 4.
Oh,
Okay, so some of you are not getting this. Okay, so let's make sure we can use this properly, okay? All right. If you have a scientific calculator, check to see if you see an answer button somewhere on your calculator. An answer, it might be above the equal sign or right next to the equal sign. Okay, so this is, to do this, all right, you have to understand your order of operations and parentheses and things. You can do this in 2 steps. It's quite simple. I mean, you can do it in 1, but I think it's quite simple to do in 2. So type in 0.1742 times parentheses 1 minus 0.1742. Okay, divided by 120 equals. Okay, so that will give you what's inside the square root, and it should be like 0.11 something.
Yeah.
Okay, good. Then hit the square root button and the answer key equals.
What was that last number?
0.11 something.
0.1.
I don't know.
And then do.
Square root answer key, and you should get this.
And then equals. No. We got 0.417.
Just like this one.
0.1742 times parentheses 1 minus 0.1742 close parentheses divided by 120 equals square root 0.00119 0.034623. I'm still getting this. Alright, who's still struggling with this? I'm willing to take the time here because this is important. So you guys are struggling over here? Okay, good.
Why do you do the answer?
Okay, so you do the first thing and then just hit the square root button. On your calculator, you can just hit the square root button. So this is if you have an answer key. Otherwise, you might be able to hit equals and then just hit the square root button, and it'll give you that.
Why do we do the answer?
Because I'm just calculating what's inside the square root, and then I'm saying take whatever this number is and take the square root of it. Okay?
So then you do square root and then it puts your.
Take the square root of whatever. So this thing comes out to be like what 0.001198 or something. All right. This is equal to whatever's inside here, and then we're taking the square root. Okay? Everyone's good. Everyone's gonna get it. If you see this on the quiz next week, which you just might, you're gonna do fine. Yes. Yeah. Can you get the first part?
No. I got it.
Enter.
Oh my god, you're gonna die on my I will show it to you, but you wouldn't understand. Whatever. I was theoretically it is the square root of function. I don't understand.
All right. Is everybody okay? Everyone's good? All right, so that is my standard deviation. So now I have a mean and I have a standard deviation. Is this okay? Yes.
And you're just telling us the mean?
Well, I'm telling you in this scenario, I'm giving you the population parameter.
Oh,
What
Okay?
if there's no mean? We don't know how much is in the
No,
breakdown.
well, we do, alright? This, what is this? This is a histogram of what?
Sample? The sample proportion.
Sample proportions. Listen up, you guys. This is important. This is a histogram of the different sample proportions. Okay?
You have to draw a histogram on the
No, you don't, alright? But I'm just trying to get you to understand where this is coming from. This represents every time I reach into my bucket, grab out 120 M&Ms, and I count how many are green, and I calculate that proportion. Sometimes I get 20% green M&Ms. Sometimes I have, 17.5% green M&Ms. Sometimes I have more. Sometimes I have less. Okay? And if I keep track of this, some of those proportions are more likely than other proportions. Yes, it's possible for me to get a proportion of 8%, but this is going to happen very, very, very rarely. Okay? And that's represented, way out here. This is like the one time where I got 8% green. Okay? And yeah, on the other end, sure, it's very possible that I got like 40% green or something like that. Yeah, maybe not 40, maybe 28% green. Okay? It's also possible, but very unlikely, especially if I'm pulling out 120 M&Ms. So this is the histogram of the sample proportions, or this is also known as our sampling distribution. Okay? This shows how the different p-hats are distributed. And I'm telling you that this distribution can be modeled with the normal distribution, where we have a mean and a standard deviation. Where my mean is this and my standard deviation is this. Okay? So now I can ask you a question. Such as, if I were to draw a random sample of 120 M&Ms out of this bucket, M&Ms from the bucket. Okay, what is the probability that this sample has over 20%, no, let's say 25% green? Does that make sense? So, I scoop out 120 M&Ms. Is it possible for there to be more than 25% green?
Yes.
Yes, it's possible. Okay? I want to know what's the probability that that's going to happen.
How many colors are there?
Oh, 0.
It doesn't matter how many colors there are.
How many M&Ms?
Huh? I'm taking out a sample of 120. I'm telling you that the population proportion is 0.1742. We've already done all the work that you need to know to answer this problem. Do we see that?
Yes.
This is exactly the same as what kind of problem from...
Normal distribution.
This is a normal distribution problem, okay? It's a normal distribution problem.
So would we look for?
And the mean is what?
The mean is 0.1742.
Yeah, so it's a normal distribution with mean 0.1742. And what's my standard deviation?
0.0346.
0.034662, whatever, okay? 623, okay? If I'm keeping a bunch of decimals. And I'm asking, what's the probability that my sample proportion is over 25%, or what is this in 0.25, right? That my sample is over 0.25 green. Are we okay? So what is the next thing I have to do?
Your table.
Okay, well, before we get to the table, maybe... Alright, we'll draw a picture. In the center, what goes in the center? 0.1742, and I'm drawing a cutoff line where?
So it's like all the way over.
Over here at 0.25. And what am I looking for? I want to know how much is shaded more than 0.25. Is that okay? That's what I want to know. So what do I have to do? I have to find the
Z-score.
Z-score. Thank you. So how do I get my Z-score? 0.25 minus 0.1742 divided by 0.034623. Alright, who's lost? You're lost. Okay. Where did I lose you? Z-score. Okay. Do you understand why I want a Z-score? Kind of? Kind of. Okay. Do you understand that this is a normal model problem? Okay. So if I had a normal model problem and I said what? Bengal tigers have a mean weight of 1,000 pounds and the standard deviation of 100 pounds, and I said, what proportion of tigers weigh more than 130 pounds? Or 1,130 pounds? What do you do? No, you don't know that?
Again.
Okay. Well, okay, so, well, this is a chapter 6 problem, okay? This is from chapter 6, and so if you didn't learn chapter 6, or chapter 6 was very shaky, okay, you've got to make sure you understand that, because we're building off of that, okay? So, you know, there was the quiz last week, and I don't know what we talked about. There was something, right? And we just said, you know, what proportion of something is over something, okay? Basically, you got to figure out where something is. You get figure out the z-score, and then based on that z-score, you look it up in the table, and that table will give you a proportion. Okay, so I just have to say study chapter 6. A little review that, okay, and we should be able to go. Yeah.
I have a question. It says it said over 20. Oh, it always said. Okay, never mind. I was thinking it said 25%.
Yeah, or 0.25 or 25%. 25% is still
Because if it was 25%, wouldn't you be looking on the table for 0.25?
No, that's
Whenever you have final.
no, that'd be a situation where I gave you the proportion already. But it's a little bit different because 25% is 0.25, but that describes our cutoff line. Okay, just go with me for this, yeah.
Are we supposed to know when to find the z-score, or are you gonna tell us in the question?
I will not tell you.
So
You're gonna
we're
find the
supposed to
z-score.
know.
You're supposed to be able to read
Understand.
this and understand that this is what you have to do, okay? And this is why I'm teaching you and telling you, if you read this, this is what you have to do, okay? Yes?
On the midterm, I got confused too. Not this where after you get the answer for the z-score, you
Uh-huh.
divide. I think it's like answers like 2.1892, and I just for the midterm I cut it off at 2.189, and I rounded it, and I did 2.19. Would that be wrong to look at the chart?
Let me
Because that's what got confusing.
No multitasking.
let me see. Okay, so I get 2.1893, okay? Or something like that,
Yeah.
okay? Now, when I look up in the z table, the z table only goes to 2 decimal places, right? So I have to round off to 2 decimal places.
Yeah, that's
okay? So rounding rules, where would I round to? I would round to
2.19.
2.19. And
Exactly.
that's correct. This is my z score. My z is 2.19.
Oh, okay.
Okay, great. And then we still have our z tables, right? From 2 weeks ago. All right.
It's 0.9857.
Okay, so I look up 2.19, and so the probability that z is less than 2.19, you said is what?
0.9857.
9857. Is that my answer?
No, don't you do one
No,
minus?
I want the proportion over.
Yeah, one
So I'm going to
minus.
do 1 minus this. And I get 0.0143. Okay? 0.0143. So, if I take a random sample of 120 M&Ms from the bucket, what's the probability that the sample is over 25% green? That will happen about 1.5% of the time. I got a probability of 0.0143.
So that's
Yeah, this is our answer. This is the probability that a random sample has over 25% green. Is that okay?
I still don't understand when I would use this versus.
So the other one you look up that score in the table if you're given a percentile.
Yeah.
But I give you a
Will we ever-
percentage, not a percentile.
Oh, okay.
Okay.
Okay, gotcha. Huh?
Okay. Let's try another example, and then we'll take a quick break. All right. Okay, so we'll do another example. You should start this example and study it, because you might see something like this on your quiz. I'll just tell you, you will. All right. Okay, so if we're not dealing with M&Ms, maybe I don't know, just something where we could easily draw random things. Okay, so let's say you've got a giant can of change, okay? Right? You've been amassing coins over here, and let's say you're going to draw a handful out of the coin. Okay, so let's say in this change thing, let's say 18%. No, let's say you just, it's a lot of pennies. So let's say 32% are pennies. Okay. It costs more to manufacture pennies than what a penny is worth. Canada, they got rid of the pennies. pennies, actually, they just round off to the nearest 5 cents. Okay, anyway, 32, let's say 32% are pennies, okay? And let's say you draw out 200 coins, okay? Take a sample of n equals 200 coins. Alright? What is the probability that less than 30% of the sample is pennies?
Are we using the same mean and standard?
No, this is something totally different, right? Okay, so let's say we have a can of coins, 32% are pennies. Okay, so see if you can answer that question on your own. As time goes on, I'll add little hints along the way. But this is how a problem might be written, something similar to this, and you should be able to answer the question just based off of this information. Okay? So don't complain to me that the quizzes are too hard, because I'm giving you a quiz problem or something very similar to it right here. Yes? You need help with the calculator? Okay, sure.
The mean is if it's a normal distribution, it's usually the mean.
But this means is the population for
But I said, but how do you know the population proportion?
that's like the mean for like the entire population. You take the mean as average of
Yeah,
the
yeah, no, I mean,
sample,
that's-
that's a different kind of.
I'm gonna do 0.32 over 200. I feel like the mean is 200.
Okay, well, I'll give you the answer, and then if you can work towards that, and then I'll also add clues along the way. Are we totally stuck? Are we able to? Yeah, we're totally stuck. No?
Can I look at your distribution thing?
You need a Z table?
Yeah.
That's fine.
Or I think the back.
Yeah. Okay, well, I'll start you off. Alright. This 0.32 is our population parameter. Okay? Is that okay?
Yeah.
And then we have a normal distribution where the mean is equal deviation, sigma, is equal to the square root of p times 1 minus p over n. Okay? So see if you can go on from there.
Okay, go ahead.
Okay. So remember, when you see the problem, it's going to be the way it was, all right? And I'm expecting you to be able to figure out the next steps on your own.
Yeah.